Welcome to module 3 of object oriented analysis and design. In the earlier modules, we have taken a look at some of the big challenges that are faced by software engineering, software projects having a high percentage of failure, and based on that in the last module we tried to look at some of the typical complexities that face software development, the issues that arise from the problem domain, the external complexity, the difficulty of managing groups, and the issues arising from discrete system behavior and flexibility and so on. So, now we slowly start getting into how to handle, how to manage this complexity. So, in the module, the current module and the subsequent ones, we will slowly start characterizing how to handle this complexity. So, first what we do in this module here is we take a look into a variety of complex systems and try to observe what is their inherent structure, what is their inherent behavior, and through that process we will try to extract some commonality that we can canonicalize at a later point of time, and then find out a strategy to handle the design, to handle the complexity. So, this current module will specifically focus to understand the structure of complex systems, and we take 3 examples, one man-made, one natural and one social system, and from that we will try to understand the attributes of a complex system. The module outline, as you already know, is presented also on the left bar of every slide. So, the first system we take a look at is a man-made system. We try to understand what is the outline of a personal computer. All of us know personal computer. So, you will know that there are a personal computer of whatever capacity you talk of. I am not talking about any specific personal computer, even this will include laptops and so on. Will comprise a CPU, which is a basic component which executes programs. It must have a hard disk to store the programs, store the data on a persistent basis. It must have a monitor to display, interact with us, the output device. It must have a keyboard as an input device, and typically it will have a removable storage, secondary storage like USB or DVD. At least these are the minimum components which will define a personal computer. Now, if we take in each one of these components, say just as an example I take the CPU, then I can say that the CPU actually comprise a number of subcomponents or subsystems. It must have an arithmetic and logical unit, which is a core unit which does the mathematical computation, the condition checking and so on. The CPU must have primary memory, the fast memory through which we operate, and it has buses that will connect to the peripheral, the external devices of a CPU. Now, in turn, again if we look at the ALU, the arithmetic and logical unit, then we can decompose and find other subsystems that ALUs must have registers, it will have control logic, it will have other say floating point unit, integer unit, branch unit, all these different components will be there, all are not listed here, it is not possible. That will comprise and make the arithmetic and logic unit. Now, again if we go deeper, look specifically into register, we know that typically today the registers are built with the digital logic of NAND gates, inverters and other different kinds of gates. Now, if we look into a particular NAND gate, typically a NAND gate will be realized in terms of a CMOS technology. So, it will have CMOS gates and interconnects. So, if we specifically look into, so this was the highest level of decomposition. So, a personal computer, if I look at it this way, here I have a CPU, I have hard disk, I have monitor, I have keyboard, I have USB. Then this CPU in turn has ALU, it has memory, another component as let us say memory here, then it has bus, all these different components. Now, if I take ALU, then again I have resistors in them. If I take resistor, I have gates in them, and so on. So, if we just keep on going on this hierarchy, you will find that the whole system can be described as a collection of hierarchical components, hierarchical subsystems, where every system has certain subcomponent subsystems in that and is a part of the higher level of systems. Now, this is what we observe in case of a personal computer. So, but at a basic level, we can see that the building block of a personal computer is something very generic. These are basically gates, NAND gate, inverter. So, whether you talk about ALU or you talk about say the memory or you talk about hard disk, fundamentally these are collection built with several primitive gates, and on the other side we have different interconnects to define the buses that exist on the CPU, the buses that connect from one CPU to the hard disk, and so on. So, while on one side the personal computer has several other systems and subsystems of complexities, on the other side there are few primitive elements through which these computers are built up. Now, with this observation about personal computer, we can try to make some generic properties, and we will slowly build upon those properties. First thing we observe is each level of hierarchy represents a layer of abstraction, which we mean is, if I talk about a personal computer itself is an abstraction, it is a concept. And so, I can say that this is at the top level of hierarchy, this is a personal computer. Now, we say that this is comprising a number of other levels hierarchically of HDD, of monitor, of keyboard, and so on. Now, the CPU in turn has ALU, it has memory, it has bus, and so on. So, what I am trying to point out is, if you look into if you look into this layer, if I look into this layer, then these different components of this layer together build up the higher layer. In turn, if you look into any specific component here, that again is built up by other subcomponents. So, each layer is built on top of other layer. This layer of CPU is built on top of this layer. In CPU, HDD, memory, monitor, keyboard all make up the next layer. So, these are just a few examples shown here of this multi-layered structure, like CMOS gates build NAND gates build resistors, and so on. But in spite of all of that, the major property is that every layer can be independently understood. I can study CPU independent of any other layer, anything else. They work independently with what we call is a clear separation of concerns. That is, when I look into the functioning of an ALU, I just assume that there is a memory to which I can send a data and keep it as long as I want. But I do not really need to know how the DRAMs in the memory, the flip flops in the memory really work to make that happen. And when I concentrate on organizing the memory, what are the different ports, how the address to be decoded, and so on, I am really not concerned with how numbers are added in ALU. All that I know is ALU might ask, the CPU might ask for some value to be stored or retrieved from the memory, and at that point of time we can just respond to that request. So, this individuality is, as we will see, can be thought of is called the separation of concerns. That is, different systems within themselves can function independently, and across systems there is an interconnection, there is an interlinking which has to be clearly specified. Further, we can make some more observations that in addition to this hierarchy and this independence of components and subsystems, there are some common services and properties that are shared across layers. For example, many of you who have little background of electrical sciences would know that if I have a CPU, then the CPU needs power, all components of CPU, the memory needs power, the bus needs power, the ALU needs power, the registers need power, and each of the component do not separately get a power. There is a power tree which kind of distributes the power to different components. This power tree is there for a common facility, common service that is shared by different components, and in many systems we will see that this particular concept will be applicable. Given all this, what we observe is we have several subsystems for every system, and when we look at the system and the subsystem separately, we find an interesting observation that if we just take the subsystems as a collection and then we put them together, then the system that we get is actually more than just the collection of the subsystem. ALU by itself can only add 2 numbers in a register and so on. Primary memory by itself can store some values, retrieve those values. The bus can only take a value from one point to another, but when you put them together into a CPU, it can execute a program. And this principle is known as the emergent behavior principle. The behavior, where we say that the behavior of the whole is greater than the sum of its parts. So, behavior of the CPU is more than the behavior of the ALU plus the behavior of the memory plus the behavior of the bus and so on. Together, when they are put together properly interlinked, then they build the whole system which has a higher emergent behavior. Finally, we will observe that the systems, complex systems often demonstrate cross domain commonality. That is, all these different hierarchy and commonality that I am discussing in terms of personal computer. If I just go to one of the modern day cars and try to look into different subsystems of steering control, brake control, air condition control, the window control and so on, we will find similar processors there having very similar kind of functionalities. So, if I understand the functionality of a CPU kind of or a personal computer kind of complex system, then that will aid me a lot to understand different subsystem of cars as well. And the same logic would apply for understanding mobile phones, understanding aircraft controls and so on. So, there is a lot of cross domain commonality that can be found. So, these are some of the generic observations that we are making from our example of personal computer. Now, let us move on. Let us move on to take up the next system, which is a natural system, and we look at the structure of plants. I am not a botanist and certainly I do not expect a whole lot of knowledge of botany, but all of us understand this much, which we studied in school, that a plant comprises primarily 3 parts. There has to be roots that go into the ground usually, there is a stem and there are leaves. Roots absorb the nutrition, the water, minerals from the soil, stem carry those from the root to the leaves, and leaves use water, minerals and the sun rays to do photosynthesis, so that food can be prepared. These are the basic. So, if I look at a plant as a system, then these are the main 3 subsystems with their functionalities. Now, again, like in the case of personal computer, we can start decomposing and look into subsystems. The roots have branch roots, they branch through the soil. There are at the end there are root hairs. At the end of the hair there is a root apex and a root cap. So, any roots can be typically thought of to be comprising of 4 different subsystems as listed here. In turn, branch roots will be comprising a collection of cells. Every cell will comprise chloroplast and nucleus, and so on and so forth. I have just expanded a few places only, just to give you a representative idea. If we expand it all, then it will really become an essay in botany. Similarly, if we look at leaves, they are formed of subsystems defining epidermis, mesophyll and the vascular tissues. Similar decomposition is possible for stems and multi-layers. So, this is what we find in a natural system, and again, if we look at how this is implemented, we see that the building blocks are few. There are cells of different types and there are vessels to carry fluid, carry information from one part of the subsystem to another. Very something that we should note is kind of very common with what we saw in personal computer, that such a complex system like a personal computer has very few building blocks like interconnects and gates and so on. Similarly, such complex systems as plants have very few building blocks fundamentally in terms of cells and vessels and so on. Now, I take you back to the same characterization chart that I discussed in terms of personal computer, the same set of points, but we just read these points now in the context of a plant system. Again, we have seen that it is hierarchic. It has different levels of abstraction, the plant being the highest level, then you have roots, stems and leaves, roots have branch roots and so on. So, each layer again is built on top of the other. You can see that cells form branch roots go into forming roots and so on. So, if you look at branch roots, it has to use cells, it is built on top of that. If you look at branch roots, they help to build up roots, and each one of them, each one of these subsystems can be independently understood like a leaf, and they work independently with a clear separation of concern. The way the roots function, they does not need to know how photosynthesis happens in the leaf, and when we study the leaf, we do not really need to understand the osmosis that happens to absorb water and mineral in the roots. Again, together we can pick up a leaf, we can pick up a stem, we can uproot a plant, but when we put them together and the system is properly interlinked, we find the emergent behavior of a plant, which is certainly bigger than the independent behavior of these components. And very interestingly, the natural world show a significant amount of cross domain commonality. For example, in parallel to plant systems, if we just study animal systems, we will find very similar hierarchy of different broad systems like digestive systems, like reproductive systems, like respiratory systems and so on. We can keep on decomposing that, but when we go to the basic building blocks, they are again cells. So, the cells differ. There are different kinds of cells, animal cells have certain properties, plant cells have different properties, but the fundamental part is they are undeniably these are cells. Those are the constituents of plants and animal both. So, across domain we find commonality here as again as we saw in case of the personal computer. So, let us just move on and take a third example, which is kind of a social administrative system, and since we all are in India and we are related to education. So, I take an example of the education system in India. So, if you look at the education system in India, if you take that as a whole system and then try to analyze, you will find that they are significantly divided in terms of centrally funded technical institutes like CFTIs, then there are organizations like University Grants Commission or AICTE who regulate higher education, and there are CBSE, ICSE and so on who regulate school education. Now, if we look into any one of these, particularly say CFTI, you will find that CFTI and IIT is like a CFTI, is a CFTI. You will find different departments, library, stadium, auditorium and so on. Every department will have students, teachers, staff. Similarly, if we go to UGC and start decomposing that, you will find universities, universities will have colleges, colleges have departments, departments have students and so on. CBSE has schools, schools have students, playground and so on. So, again we see that in a system of social, political, administrative nature, we again see the on one side we do see it's a really a complex system again, but it again shows the same kind of hierarchy, same kind of system subsystem decomposition that exists. Building blocks, there are in the education system there are few building blocks. One is the knowledge delivery, that is how people teach. One is examination, how the knowledge acquired is checked, and how people join these institutes and how they graduate and go out of the institute. If you look into all of these institutes in the educational system, you will find that these are based on defining or specializing these specific building blocks on which then you add different variabilities, conditions and terms to build up these systems. So, we will be back to our characterization of complex system, the same slide. Now, we are interpreting this in terms of the education system of India. So, again the highest level of abstraction is the education system in India. Below that we have CFTI and UGC and all those, and then the appropriate ones. For example, if we look into this particular, that departments build up colleges, colleges build up universities. So, if we look at colleges, then it is built in terms of the layer of departments, and colleges go in terms of building the university layer. So, the similar kind of structure that we had seen for a personal computer and system and the plant system, we do see here. We do see that these systems, many of the systems can be independently understood. There is separation of concern, the department and library has to function together, but how a department functions and it conducts its classes and examinations and all that is not required to be understood by a library system which has procurement of books, issue of books and so on, and vice versa. So, they enjoy a whole lot of common services like NKN is available between institutes, the many departments, but they are they use the same telephone system, and finally, they demonstrate the emergent behavior. When we just take the library separately, the department separately or the playground separately, we have certain functionalities, but when we put them together, then we have a college which has a bigger functionality. When we put 100 colleges together under a university, we have a different kind of additional behavior. And certainly, also in terms of cross domain functionality, we find that different practices, different properties that are held in the education system are also enjoyed by several other. For example, the leave policy of teachers and staff will be lot similar to the leave policy of teacher and staff in public sector institute PSUs. So, in short, what we want to conclude from these examples is that there is a whole lot of similarity between all these different kinds of system, irrespective of whether they are man-made, they are natural, they are social, or of other kinds. So, just to recap that we saw that every system has a few primitive building blocks, personal computer, plant, education system, all of that, and just putting everything together, that complex systems are hierarchical and they demonstrate a whole lot of properties which are independent of whether it is a man-made system, it is a natural system or whatever kind of system. Complex systems typically show these properties. So, these are collection of all the instantiations for your easy reference, and I have some additional ones also included here, but I will just clean up and show you. This is the take back we want to do from this short study of structure of different complex systems, that to summarize, complex systems are hierarchical. This is a major observation we are making, and it has multiple layers of levels of abstraction, and levels of abstractions are interrelated. Every level supports the higher level and is supported by the lower level. Every level can be understood on its own. The different components in a level have separate concerns which can be independently studied. Put together, every level build up a bigger functionality for the next level, and there are a lot of cross domain commonality in terms of these systems. So, we started with the issue of how we actually handle complexity, and this was our first step to go forward analyzing the complex system, and through some examples we analyze and come to the conclusion that while the complex system are indeed complex, but they do show a lot of common properties. So, if we build up strategies, if we build up further analysis based on these properties, based on these characteristics, then we hope to be able to analyze a new complex system lot more effectively. So, with this intention, we go forward to just put all these observations in a very crisp terms, and this is typically called the 5 attributes of complex systems. That every complex system will have hierarchic structure, and this hierarchy will terminate in a primitive which is directly defined. Now, what is a primitive and what is not a primitive is kind of a subjective decision. There will be strong separation of concern between these components. Across domains, there are similarities. So, there are common patterns that happen across domains, and the whole development of such complex systems has to happen through a iterative refinement process. So, at every stage we will need to have certain intermediate forms. So, just to quickly illustrate a hierarchical system, we have been talking from the beginning of this module, we have been talking about these systems. So, they are composed of interrelated subsystems, subsystems and so on, and at the bottom they have elementary components. And we can understand now, you can question that is it necessary that all complex systems be hierarchic in nature and show this behavior. The reality is that the complex subsystems that we study do show this behavior, or we can put this differently, that only those complex systems we can study and try to think of putting up a software system on where this hierarchy exists. So, it is kind of our basic assumption is hierarchy is the kind of baseline, is kind of the foundational part of a complex system, and on which the remaining 4 attributes are built up.